Now op amps. General purpose op amp, the 741 is probably the most popular. I don't know if it's the oldest, it's just the most popular general purpose one. The idea behind the op amp, to start with, you have to understand the basic functionality of the op amp by itself. And that is all built into this equation here. The output, right here, is just A0 times the difference in the inputs. The inputs VP here, this is called the non-inverting input. You'll find out why in a moment. VN here, that's the inverting input. Same, find out in a minute. All these numbers, 2, 3, 4, 6, those are all over here. This is an example of an actual op amp that is quite common. So this gain term, a typical minimal value for that gain is around 10,000. So you'll see in the spec sheets for these op amps at least 10,000 or more. The way that this op amp works, let's say VP is 5 volts, and let's say VN is 4.99 volts. Then that means, if I can move this over, V out wants to be 5 minus 4.99 is 10 millivolts times 10,000. So we have 10,000 times 10 millivolts, and that is 100 volts. So it wants to be 100 volts, but I don't have 100 volts to work with. I have the supply volts, the supply values here. And typical supply voltages are something like 15 minus 15, or 9, plus minus 9, whatever. So this 100 volts is obviously not going to work. If we design it to expect 100, we're only going to get 15. So it rails out. That's what these are the supply rails, plus and minus 15, or whatever they're the highest voltages, the highest and the lowest voltage in the circuit. They have to be. You're always going to design your circuit such that these are the highest and lowest voltages. So your inputs, you don't want them to be any higher or lower than those values. So it's just going to hit 15 volts for any small difference in the inputs. What about if this is 4.99 and this is 5? So now it's going to be the same 10,000, and now we're going to have a difference of minus 10. So this wants to be minus 100 volts. And of course it's not going to hit minus 100 volts because we don't have that much to play with. It's going to hit minus 15. It's going to rail out at minus 15. So if I just say here we have VP and here we have VN, then my output, Vout, everywhere VP is bigger than VN, my output is going to rail out to the positive plus rail, in this case 15 volts. And then anywhere VP is smaller than VN, it's going to rail out at minus the negative rail, and so on and so forth. So it's always just this square wave. That's how this op amp wants to work by itself. You're never going to design this around 0. You don't want this 0 volts here because it's unstable. If you're designing your circuit to use just the op amp functionality by itself, it's called a comparator. Just this is called a comparator. But you don't build a comparator to operate around 0. You always make sure that the values that you want to compare always rail out. So then what good is it if we're always going to rail out? So a non-inverting amplifier takes the op amp and it puts a input. Let's call this VP here. These are all resistors, if you can't tell. We have an input voltage source on the plus side, the non-inverting side. You get the hint, it's going to be non-inverting. The trick to analyzing these circuits is to realize that you never have current going into the op-amp on the inputs. So these are always zero. Call this Vn. So with those being always zero, if I take and arbitrarily label a current going this way, I could have labeled it going the other way, it doesn't matter. Like I said, just choose a direction and go with it. The numbers will work themselves out, positive or negative, however they're supposed to, based on the values you choose. So if I have current here, how do I solve this circuit? Well, I have VO. Let's draw this as a regular circuit looking thing. So Vout is acting as an ideal source. It's just supplying power coming out of its output here. It's not connected to anything yet. It just has this negative feedback, and I'll discuss in a minute why this is so critical. This feedback from the output to the Vn, the inverting input. So this op-amp is acting as an ideal source right here at the output. So if I follow Vout, go across RF, then this node here is this node here. So that's I'm going to label that as Vn. Then to ground, I have RS. And this current, if I label it the same way as that, it goes like this. Here's the critical thing. In order to relate these values in this circuit to something useful, namely in order to relate Vout to Vin, see if I have Vout over Vin, that's the gain of my circuit. That's the definition of the gain. However much you put in, multiply it by the gain, that's how much you get out. So I need to find this relationship. With this circuit drawing here, I can find a relationship between Vout and Vn. But I need to make a relationship between Vn and Vin somehow. This just adds unnecessary complexity. The way I do that is to realize that this op-amp actually wants to do this. That's what it wants to do. If I just start with assuming Vp is greater than Vn, then knowing how the op-amp by itself works, if Vp is greater than Vn, because of this huge gain, I'm just going to hit the positive rail. If I hit the positive rail on this circuit right here, that's the highest voltage that I have available on this entire circuit. Because remember, the highest voltage and the lowest voltage are here. Those are my plus rail and minus rail, and those values determine what I'm getting on the output. So my output here, it wants to act like this. So that high value is sensed by this Vn, this non-inverting or this inverting input, because of this feedback. Sure, there's a divider here. It's getting, it's losing some energy here to get to here, but this argument works just fine as long as Vp and Vn are close enough. Because this high voltage here being fed back increases Vn to now be bigger than Vp. So the assumption was Vn was small. The assumption was Vn was smaller than Vp. Because Vn was smaller than Vp, we hit our positive rail. That makes it so that Vn is now bigger than VP. And because of that, we hit our minus rel. So notice that no matter which one I started with, whether I started with this assumption or started with this assumption, it would have gone to the other one naturally. So I'm just going to go back and forth, oscillating here until what? Think about what's going to stop this from oscillating. There's going to be some stability criterion to stop this from oscillating, and that criterion is when VP equals VN. Because otherwise VP is greater than VN or VP is less than VN, and in order for that oscillation to stop back and forth, then VP equals VN. And that's what happens. The negative feedback stabilizes the output such that VP equals VN. So that allows us to relate this VN to now VP. So we know that VN equals VP, so that this node now we can call that VP. Now how do we relate VP to Vin? Well, here's VP, here's Vin. And by the way, when I say VP, if I say a voltage here, it has no meaning to say here's a voltage. It's always here's a voltage with respect to something else. Voltage at this location with respect to another location. So voltage here with respect to ground. That's the definition of a node voltage. So anytime you're looking at a circuit and somebody puts a probe somewhere and says, what's the voltage here? It means here with respect to ground. Here with respect to ground. Whichever, these are all the same common ground. So all these voltages are all with respect to ground. Vn is with respect to ground. Vp, V0. So if I have no current here, remember the inputs don't accept a current. I have no current across this resistor. According to Ohm's law, if I have no current across a resistor, then I have no voltage dropped across that resistor. I have no energy lost across that resistor because there's no current. So that means my Vp equals Vin. So let's use another color. Vp equals Vin. So now we can relate Vin to V out through this circuit here. Well, Vin, the voltage here with respect to ground, is across this resistor. That's the voltage across RS. So looking at this current through both resistors, I'm trying to find the voltage across one of the resistors. That's what I just did before the voltage divider. So go back and review the voltage divider and see that I have V in, which is the voltage across here, is equal to V out. That's the voltage that is being divided across both resistors. And then the divider equation it's across RS and the total resistance in the branch. So now if I want to get my gain term, my gain defined as V out over V in, if I rewrite this in brackets, it's it's essentially the inverse of that in brackets. That's my gain term for the non-inverting amplifier. So now the inverting amplifier. It's always going to have negative feedback. That's what stabilizes it so that we can say Vp equals Vn. That's always the case for negative feedback. In is equal to 0 for all the op amps. That's the ideal circumstance that we have to consider to solve these circuits. Here's VP, here's VN. Now RS, I used to have the source on the input on this side, on the VP side, but now I have to figure out how to put it on the VN side. Where would be a natural place to put it on the VN? Well, if I tried to put something here, even if I put a resistor here, before I had something over here, but now I'm going to have to ground this because I have nothing there. I can't just let it float. So my VP side has to be grounded. That means my VN has a virtual ground because of this VP equals VN. That's always the case for this negative feedback. This negative feedback ensures that that's the case. So if my VP is grounded, and remember there's no current, so this resistor does nothing. If my VP is grounded, that means my VN has a virtual ground on it. It's at 0 volts. And if this is always at 0 volts, what good is this VN going to do being right here? This is always 0 volts. So no matter what happens here, there's nothing happening here. So this does nothing. So this has to be gone here because it would do nothing right there. And same thing over here. If I tried to put this guy on the output, then my input would be tied to the output. That would be stupid. So it has to. The only other place that it could be is right here. So now let's do the same analysis we did before. Draw an arbitrary current. I know that my current has to go down. There's no current going into my inputs, so it doesn't branch off. So if I draw this as starting with V in, I have V in. I go across RS. That gets me to this node, which is the VN node. Across RF. And that gets me to V out. And of course these are all, Vn is the voltage relative to ground, or common. Same with V out. It didn't have to be that way. I mean, this Vn could have arbitrarily been floating somewhere, but then we would have had to redefine what it meant to be the voltage right here with respect to ground, because that's what we're trying to find, the relationship between V out with respect to ground relative to something else with respect to ground. So we're going to find an effective way of writing some voltage with respect to ground anyway. So we have Vn equals Vp equals 0 volts because it's grounded. It's got a virtual ground, so we're just going to add that right there. If I follow the current, it starts at V0, goes like this, and like that. Notice that this current goes through this node. It goes directly through this node, and you never get a current going into the ground. It's easy to see that that current only goes through this, so that node is the same as this right here. It's easy to see that this node doesn't go, it doesn't have any current branching off anywhere else. But what I'm talking about is, because this is grounded, this is virtually grounded. So I could have drawn this anywhere. I could have drawn it up here. It doesn't matter where I draw it. It's just a label. It's just saying it's grounded. It's 0 volts right there with respect to the rest of the circuit. So I'm at 0 volts with respect to the rest of the circuit, but it doesn't, just because I've drawn this in here, it doesn't mean that I can allow a current to go through there. I can't just arbitrarily start sending currents through labels. Same thing here. I can't just arbitrarily send a current through there. So we've decided that this current definitely goes directly through the node and continues. So then I can relate the current here to ground to the current here from ground through this source. I'm just going to rewrite this current I. It's I right here. And it's I right here. So notice the voltage across this resistor, it makes sense to label it this way, positive on the top, because then I can, I mean, it's just arbitrary. I could have done it backwards. It doesn't really matter, but it's better to do it this way because I already know that I have my V in is plus minus there. I have V in volts going from here, dropping down to here. But notice this current, so if I have a resistor that I'm trying to use Ohm's law across, and I make some assumption about the polarity of the voltage across it, then if I go in and I label the current through it, you always cross the tail and put a minus on the head. Notice that these pluses here are the same, and they're on the same side, and the minuses are on the same side. So then you can use Ohm's law, IR, whereas if it was backwards, if I had labeled the polarity this way, and I had said that my current was going this way, then notice that the polarities for the currents and for the current and the voltage are opposite. So then it's going to follow minus anti-Ohm's law, if you can call it that. So as long as the arrows are pointed the same, as long as the signs are on the same side of the resistor, then we can use Ohm's law. So let's use Ohm's law across wherever we can, anti-Ohm's law wherever we have to. So we have voltage across RS is Vn, it's the same voltage across both of them, equals minus I times RS. So then solve for I. So then on this other, on the right hand side, we have VRF is equal to V0. And the voltage across RF is just I times RF. So then solving for I, we have the same current here. We have, so that's our inverting gain term. What use these have in general. So let's say you have an input that looks like this. Then the inverting amplifier, let's say you have a gain of 3. The inverting amplifier is going to amplify this by 3 and invert it. And then the non-inverting is obviously the exact same idea, but it's just not inverted. But what if we wanted to do something like take the difference between two different signals, find a difference amplifier or a summing amplifier or whatever? And then we have to start introducing this linearity concept. It has two properties: superposition, which mathematicians call additivity, and scaling, homogeneity. So the idea here is for superposition, if you have some input, I'll just call it X, special X. If we have this input into a circuit, a linear circuit, which I'll call T, then the output, called Y, is going to be T acting on the input. So if we can write this input as a sum of terms, and if we can act on each one of these terms individually, such that this y ends up being the transformation of each one individually, then this system defined by t is linear in x. It's linear in this representation of x. It's linear in these components, the x0, the x1, and so forth. So the way that I've decomposed this, it's linear in that. So what we're going to be looking at is cases where, say, this x0 is v0, some voltage source, and say this is I1, and then V2 and I3, whatever. Then whatever sources we have driving the circuit, if the circuit is linear in those sources, then it's just going to be the output due to each one of those individually. So in the cases that I'm giving you here, these are all actually just V. So we're going to say V0, V1, and so forth. So that's the superposition principle. Then scaling is a lot easier if you have x is equal to some multiplying factor on a, now we can say that these x's, the reason that we want to do this is because we want to be able to define the x's as being normalized, so their value in some way of explaining it is just 1. The length of it is just 1. So then we can define the amplitude of each of these x's in the k's instead of in the x's themselves. So then the scaling property says that put these into your linear system, then you're going to get out the transformation of these guys individually is equal to the scaled transformation of each of the basis elements individually. So the k's come out, in other words, the k's factor out. Okay, that's linearity, superposition, and scaling. For this entire lecture, the most important thing is superposition. It's also important to understand how scaling comes into play for linearity.